All right, we've learned how to assign oxidation numbers. We've learned how redox reactions work within a galvanic cell. And today we're going to learn how to balance redox reactions. This can be a whole lot more complex than what we're going to go into. Again, if you take a second year chemistry class while you're in high school, or if you take chemistry when you're in college, this is just the very, very beginning of how to really balance a redox equation. So we're going to just do the real bare bones basics of it. So let's look at the first equation that I have up here. I have an iron 2 plus ion plus chlorine diatomic molecule yields Fe3 plus Cl minus. Now you're probably looking at this going, Mrs. Thompson, this is not difficult. There's one iron on each side, there's two chlorines here, so let's just stick a 2 there, and it's good, right? If it were only that easy. You balance the atoms, but the problem is when you have ions involved, you have to balance charges as well. So if I look at this side of the equation, I have an overall positive 2 charge on this side of the equation. But on this side, I have a positive 3 here, and 2 negative 1 charges here, which means that on this side I've ended up with a positive 1. So this side has a positive 2, this side has a positive 1. That most certainly is not balanced. And we have to make sure charges are balanced because we have to gain and lose the same number of electrons. You can't gain more than you lose, you can't lose more than you gain. So what are we going to do with this? I am going to write what are called half reactions underneath here. When you are balancing these, if you can do it in your head, you don't need to write the half reactions for the relatively simple redox reactions that we're going to be doing. Okay, if it helps you, most certainly may. I'm writing it out here just so that it's a little easier for you to see. So here I am going from an Fe2 plus to an Fe3 plus. How many electrons did I have to lose to go from here to here? Well, to go from a positive 2 to a positive 3, I had to lose 1 electron. Okay, now here I'm going from a Cl2 to a Cl minus. If I'm going to do that, the first thing I'm going to have to do is I know that I'm going to have at least two of these in order to balance the number of atoms, so I'm going to do that first. Now how many electrons is this going to take? I'm going from 0 to a negative 2, so that means that I have gained 2 electrons. So what that then tells me is that since I've gained 2 here and I've only lost 1, I'm going to have to multiply this piece of it by 2 in order to make my charges balance. So let's go up in the top equation and let's put a 2 in front of here and a 2 in front of here, and let's see now if everything has worked out correctly. Oh, and since I put a 2 down here to balance the atoms, I'll have to have a 2 here as well. Okay, so let's double check and make sure that this is going to work. My atoms are balanced. I have 2 times a positive 2, which is a positive 4 on this side. On the other side, I have 2 times the positive 3, which is a positive 6. I have 2 times the negative 1, which is a negative 2. A positive 6 plus a negative 2 makes a positive 4, and I already said that I had a positive 4 on this side. So this equation is now balanced. It's balanced both according to atoms and according to charges. Okay, let's try another one. Here I'm going from an iron 2 plus to an Fe. Here I'm going from an Na to an Na plus. According to the number of atoms, this is already balanced, but it is not balanced according to charge because I have a positive 2 here and I have a positive 1 over here. So let's analyze this according to what's going on in each half reaction. Again, you don't have to write this out if you can do it in your head. So I'm going from an Fe2 plus to an Fe. How many electrons did that involve? I'm going from a positive 2 oxidation state to a 0, so that means that I had to gain 2 electrons in order for that to happen. For my sodium, I'm going from a sodium at a 0 oxidation state to a sodium with a positive 1 oxidation state. And in order to do that, I had to lose 1 electron. So since I have to gain and lose the same number, that means I'm going to have to double that in order to make everything come out right. So I'm going to go through and I'm going to put a 2 here, and I'm going to put a 2 here. Now let's see if everything's balanced. Atoms are all balanced. I have 1 iron on each side, 2 sodiums on each side. I have a positive 2 on this side, and I have 2 times a positive 1, which is a positive 2 on this side. Okay, we'll try one more down here. I'm going from an aluminum 3+ plus a zinc to a zinc positive 2 ion and an aluminum. Okay, again, it appears to be balanced as far as number of atoms. It is not balanced according to charge because I have a positive 3 on the left, positive 2 on the right. So here I'm going from an Al3+ to an Al. How many electrons did that involve? Well, going from a positive 3 oxidation state to a 0 involves 3 electrons. Okay, I actually had to gain 3 electrons here. For my zinc, I'm going from a zinc to a positive 2 zinc ion, and so that means I had to lose 2 electrons down here. In this particular case, 3 and 2, I'm going to have to say, well, the least common multiple of that is a 6. So in order so that I have the same number of gained and lost, I'm going to have to multiply this by 2 to get 6 electrons, and I'm going to have to multiply this by 3 to get 6 electrons here. 6 electrons gained and 6 electrons lost. So all of my aluminums need to be multiplied through by 2. And all of my zincs need to be multiplied through by 3. So now let's double check and make sure I have the right charge. 2 aluminums at a positive 3 makes a positive 6. And then on the right hand side, 3 zincs at a positive 2 also makes a positive 6. Okay, so I've gained 6 electrons and I've lost 6 electrons. So as you're balancing redox reactions, you have to make sure that you have balanced not only atoms, but also charges.